Hello and welcome to another session in physics. In this session we'll be talking about electromagnetic induction. It has two parts, 1 and 2, but we'll be focusing on the one aspect, the first aspect of electromagnetic induction. But before that, let us review the previous lesson. Welcome back. In this session, we'll be looking at things such as induced current, and we'll be talking about electromagnetic induction extensively. In our past few lessons, we've been talking about the interactions between electricity and magnetism and their importance when it comes to the generation and transmission of electric current as we know it today. How we're able to use generators and motors in our houses to convert AC to DC and vice versa. And how to convert electrical energy to mechanical energy, and also how to go in the reverse, converting mechanical back to electrical energy using dynamos such as electric motors and generators. Alright, before we proceed, remember that we said that there are basically three methods of charging a body. The first is by contact, the second is by friction, and the last is by electromagnetic induction. These are the three methods of charging a body. We said by contact, you can charge a body by contact when you bring a charged body very close to a neutral body or the body you would like to charge. Let two of them be in contact with each other. Much like when you touch a hot pot or a hot frying pan, you're bound to feel some sort of burning sensations in your palm as a result of the fact that your body is in contact with that burning or hot substance through a process called diffusion, where substances or molecules flow from regions of higher concentration to regions of lower concentration. Alright, then the second method of charging a body is by friction. We talked about the examples of an ebonite rod and foam, and then we have glass rod and silk, and how when both of them are rubbed with each other or against each other, opposite charges are induced in these two separate materials. And we also talked about using something like a pen to rub the tip vigorously on your desk, on your clothes perhaps, and then you get a very tiny piece of paper, and you'll see that the tip of the pen here will attract this paper. That is friction. Then by electromagnetic induction, we mean charging a body by bringing it very close to a charged body, but there should be no contact between the two of them. For instance, if you are feeling cold and you want to feel warm, you don't have to jump inside the fire or touch fire. No, not at all. But you can go close to a fire. There doesn't have to be a contact between you and the fire before you can feel warm. You get close to the fire, you get close enough to feel the heat sensation, then definitely you are going to feel warm. That is exactly what happens in electromagnetic induction. Get a neutral body, a body that is not charged, and bring it in contact with a charged body. Let two of them not touch each other, but bring it very close. Let the proximity be actually very close. Close enough that charges can be induced in the neutral body. So, put simply, electromagnetic induction is the production of electric current or voltage in a conductor whenever there is a relevant or relative motion between the conductor and a magnetic field or a magnet. The production of electric current or voltage when there is relative motion. Notice the word motion, not contact. There is motion or interactions between the conductor and a magnetic field. The current that has been induced is called induced current. Now, induced current and induced EMF depends on about three different things. The first is the speed of motion of the magnet. Like we talked about in our previous lesson, we said Michael Faraday discovered that when you get a solenoid and you get a magnet of two polarities, north and south pole, or one polarity maybe, very close to the solenoid, and a galvanometer is connected across, current will be induced, which will cause the galvanometer to deflect in a certain direction. The faster the speed of motion between the magnet and the solenoid, or the coils that have been wound, the copper coils, the faster the motion between both of them, the larger the deflection of the galvanometer, which shows that the induced current is large. Another thing that affects the induced EMF or current is the number of turns of the coil. And then thirdly, one thing else that affects the induced EMF or current is the presence of a soft iron core inside the coil. The presence of a soft iron core inside the coil. Now notice here that the induced current, its direction reverses when the direction of motion of the magnet or coil is reversed. So what it simply means is that the direction of the induced current is directly proportional to the direction of motion of the magnet or coil. Now this is exactly the diagrammatical representation of what we are trying to talk about. When this magnet is put inside the solenoid or copper windings and it is slowly brought out, current is known to show itself here, and it deflects this galvanometer to show us that there has been an induced EMF or an induced current. So the faster the movement of the magnet against the coil, the heavier the deflection, and the slower the movements or the interactions between them, the smaller the deflection of the galvanometer. Alright, so you notice here that current will flow in a galvanometer whenever there is relative motion between the coil and the magnet. Such current is called induced current, while the phenomenon is what we call electromagnetic induction. Either way, relative motion could be whether the magnet moves towards the coil or away from the coil, or when the magnet is stationary and the coil is moved away. There are two laws that govern electromagnetism. The first is Faraday's law of electromagnetism, and the second is Lenz's law of electromagnetism. Now let's talk about Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction states that whenever there is a change in the magnetic lines of force, EMF is induced. Whenever there is a change in the magnetic lines of force, EMF, electromotive force, is induced. Also, the strength of that EMF that has been induced is proportional to the rate of change of the flux linked with the circuit. Now, there are a number of factors that affect the linking of a coil in field lines or with magnetic flux. The magnetic flux or field lines linking a coil depends on about three things. The first one is the magnetic field strength. The second is the number of turns of the coil, and the third is the area of each turn. So for you to obtain a large induced EMF, you have to move at a high speed across a strong magnetic field. Faraday's law gives us the magnitude of the induced EMF. Alright, let's talk about Lenz's law of electromagnetic induction. Lenz's law of electromagnetic induction states that the induced EMF is in such a direction as to oppose the motion or change the force producing it. Interestingly, Lenz's law gives us the direction of the induced EMF or induced current. Alright, at this point, let's talk about what we call an induction coil. An induction coil, put simply, is an electrical device that is capable of producing a very high intermittent EMF by electromagnetic induction. I'll take that again. Induction coil is an electrical device that is capable of producing a very high intermittent EMF by electromagnetic induction from a low voltage DC. Put simply, a low voltage DC is a direct current source such as a battery or a simple cell. A battery or a simple cell is able to provide enough EMF or voltage required or capable of producing electromagnetic induction. An induction coil consists of about 3 different things, the first of which is a primary coil. A primary coil that is made up of a few tons of thick copper wire wound on a laminated soft iron core, much more like a solenoid. Yes. And then the lamination of the core is important for us to reduce what we call loss of energy due to eddy currents. Remember, sometimes in a transformer or sometimes in electromagnetic fields, we can have energy loss as a result of eddy currents. And then secondly, an induction coil is made up of a secondary coil overlapping the primary coil. It is made up of large number of tons of insulated thin copper wire. The ends of this coil are connected to an adjustable spark gap created by 2 adjustable brass rods. An adjustable spark gap created by 2 adjustable brass rods. Now let's talk about the third one. The third component of an induction coil is found in front of the soft iron core of the primary coil, and it is a make and break device consisting of soft iron armature. At this point, we should know what an armature is. An armature is a split ring that has been divided into 2 segments, of which we can use it to change AC to DC in a generator. Alright, so this soft iron armature is carried on by a light brass spring to which is attached a platinum contact with adjustable screw. The primary circuit is then completed from this contact through a key and the battery, which provide a current. This induction coil is commonly used in motor car ignition systems and in the operation of X-ray tubes. So you can see that the importance of induction coils in electromagnetic systems cannot be overemphasized. If you want more information on this, make sure to visit the notes attached at the end of this video, and thank you for joining us in this lesson. To refresh your memory of what we've just discussed, please take the test that will appear on your screen.